thanks very much for inviting me to give this talk to you today. It's a real pleasure. So yeah, as Mark said, I'll be talking today about microbial electrochemical technologies, present you some data we have about how these technologies can be used towards opening a pathway to a net zero wastewater treatment. To begin with, is the reason we are doing all this. As you all know, our conventional sources are depleting, and right now we are faced with an energy crisis, and also another crisis that we don't speak so much about is the sanitation crisis that we face as a planet, that really comes down to how we dispose of our waste and our wastewater. Overall, in the UK, 3% of the electricity that is consumed is consumed from activated sludge treatment processes. That's not the whole percentage of the whole wastewater treatment. It's just specifically for activated sludge process. Of course, for the whole industry would be much bigger. And also right now we have around 80% of the world's wastewater that goes into receiving waters untreated. And this is a big issue, especially for developing countries. But also we've seen some troubles in developed countries with overflowing sewages that again can cause contamination of our waters. And that's mainly the reason why we're doing this research, really trying to address these two burning issues. So can we look into wastewater as a resource instead of a waste? And the reason we're asking this question is because right now we are using alternative resources such as solar, wind, or water. So what about diverting our focus and including wastewater in this equation? Because wastewater is an energy-rich waste stream. It has about 16.1 kilojoules per gram of COD, and the activated sludge process itself uses about 2.5 to 7.2 kilojoules per gram of COD to treat this. So you consider that we have the energy in the wastewater itself to actually match that. And looking at the bigger picture, in the UK specifically, there are around 11,000 megaliters of sewage produced per day, and those are treated through our wastewater treatment processes, and they cost around 750 kilowatts per hour per megaliter. So by only using 10% of the energy that is intrinsically in wastewater, we can save up to 2 gigawatts per hour per day. So that's where this whole concept comes into play of how can we really unlock that energy in the wastewater. And the answer comes from Microbial Electrochemical Technologies, because they can retrieve that energy and some part of that energy. So for those who don't know, Microbial Electrochemical Technologies is an umbrella term that covers technologies who have the unique ability to use microorganisms in order to transform chemical energy into electrical energy by using what we call electroactive biofilms. There are different technologies under this umbrella, but the two most popular ones and the most heavily researched are microbial fuel cells and microbial electrolysis cells. Microbial fuel cells use wastewater as their feedstock, and they by breaking it down, they produce electricity during the process. Whereas microbial electrolysis cells, they are supplemented a little bit with voltage, and they can split, they can generate hydrogen in their cathode side. But again, while sanitizing the wastewater. And in my whole presentation, I will speak about how these two technologies right now are making a real impact towards reusing waste and recovering resources from it. So let's start with microbial fuel cells. As I said, microbial fuel cells treat wastewater and generate electricity. This is done, the concept of microbial fuel cell is like a normal battery. It has an anode, has a cathode and it has a membrane in the middle. So in the anode, it's where we have the wastewater or any other organic matter. Bacteria grow electroactive biofilms on the electrode that is present into the anode compartment, and then through the digestion of the organic matter, bacteria release as byproducts electrons and protons. Protons diffuse through the membrane to the cathode side, whereas electrons go to the cathode side, where this circulation of electrons is what we capture as electricity. And the important thing to stretch here is that microbial fuel cells have unlimited life. As long as the bacteria are kept fed, as long as we supply them organic matter and carbon energy sources, they will keep producing current, they will keep producing electricity. And on the cathode side of the microbial fuel cell, we can have open to air cathode. So the protons from the anode are combined with oxygen, and we have the production of some water. And again, as you can see from my graphic over here, the more they degrade the organic matter, the cleaner they get it. So both treatment and electricity. Microbial fuel started about in 1911 by Michael Potter from the University of Durham, actually, but it wasn't taken up as a technology. It wasn't regarded as something really novel up until the early 2000s, when climate change and environmental damages started getting more attention. And as you can see from this graph, which derives from a study that we did with one of our environmental engineering master students, Hannah Bird, last year, the projection of the publications around the subject is increasing so far. Every year there are more and more publications around the subject, which reflects the interest of researchers around this field. And something else more important is that right now, microbial fuel cells is not only contained in labs. Since 2008, microbial fuel cells started getting out there into the world. They started to be tested in pilot trials. And the first one was in 2008 from the University of Queensland, where they built big microbial fuel cell reactors to treat brewery wastewater from Foster's Brewery. And this was the first ever exit, let's say, of microbial fuel cells from the lab into the real world. And since then, even though the numbers are not as high as the lab scale fuel cells, since then we have seen increase in the number of groups around the world that are devoted into turning microbial fuels into taking microbial fuel cells in field trials and large scale. And I was very lucky to work in my PhD and postdoc with one of these technologies, which I will show you in a minute. That started around 2014. So through the study that we did with Hannah, what we wanted to do is to see what's the results of all these pilot scale studies around the world, because they all differ in terms of material, sizes, waste streams. So we took all these 30 pilot scale microbial fuel cell studies, and we compared them against the same parameters. Four parameters for wastewater treatment to evaluate wastewater treatment efficiency, and another 4 parameters to evaluate their energy recovery efficiency. And what we see from the results, it was that we can develop a clear framework of how these technologies can behave in the real world, which is very useful if a water company is interested to uptake the technology, because they need to know beforehand, before building up the pilots, what the return will be in terms of efficiency and in terms of treatment. And as you can see from the heat map on my right-hand side, which combines the different parameters together, and the darker the color, the higher the percentage. So in the middle, we have the COD removal. And as you see, all of the studies exceeded the COD removal rate, which is around 75% based on EU standards, because we need to get the COD at about 125 milligrams per liter in order to be able to to be released. So all of the studies reached that limit and even exceeded it. However, that wasn't the case when we see at the final column of the heat map, which is the energy recovery. The systems were able to recover some of the electricity that theoretically was available to them, but it wasn't as prominent as the treatment. So overall, they were much better at treating the wastewater, and they were able to also generate some electricity to supplement the process. From all the results that we collated together, we were able to estimate how big as a microbial fuel cell system can be in a real scale. And as I said, that's really important for the uptake of the technology. So by setting the number of people that the treatment plant serves, and in that example is around 5,000 people, we are able to see the person equivalent influence of wastewater, then estimate the COD reduction based on the European standards, and then calculate what the hydraulic retention time of the system needs to be, and find out what the volumetric treatment rate and of the system will be, and the organic loading rate. So these are numbers that companies need in order to be confident towards the technology. And from all these calculations, then we're able to see, okay, how big do I have to have my microbial fuel cell tank in order to operate? And then in this example, with the hypothetical 5,000 people village, let's say, we can see that to reduce by 69% the COD of the wastewater, we will need a microbial fuel cell reactor that has a capacity of around 700 cubic meters. And also you can find what the hydraulic retention time of this liquid needs to be. Like I said before, during my PhD and postdoc work, I worked with a microbial fuel cell pilot system called PPower. PPower uses microbial fuel cells to treat urine, because urine is another contaminant of the water stream, and especially it's a problem in developing countries. So PPower, the idea is that it's a toilet that has underneath it fuel cells. The fuel cells feed on the urine provided to them from the toilet, and this can generate electricity to power up the lights inside and outside the cubicle. And we tested this technology. We tested it in the field, initially at the university campus, but then moved on to Glastonbury Festival because we wanted to test the ability of the system in a larger context. And Glastonbury Festival, for those who don't know or not from the UK, it's a huge festival, very popular in the UK, which has about 200,000 people for 3 days throughout the festival. And of course, they need toilets, all these people. So PPower was set up at Glastonbury Festival, and every year it was getting better and better because every year the system was improved through the different pilots. And as you can see from the photos on your right-hand side, you can see during night the lighting inside the toilets, which was all provided from the microbial fuel cells based on the night sensor that there was on top over here. And also this is the demo on the outside during the day as well. Then, of course, the Bill and Melinda Gates Foundation and OXFAM, which funded this project, they funded it because they wanted to have PPower urinals in developing countries in the real world. And that's when we did our trials in Uganda. So that's the photo over here, where in a village in Kisoro, they had a boarding school, and the girls that were using the toilets at night, because they didn't have light, they were quite vulnerable. They were scared from different intruders, and they didn't feel safe using the toilet. So then we partnered with them and built a shed, a unit, where we had microbial fuel cell stacks in there, that they were treating the urine coming from the toilets, and they were powering up the lights inside and outside of the toilet block. And then we went to Kenya, to Mathare North slum, where again there was a school over there that had toilet blocks but no lighting. So what we did is that we installed a newer version of an upgraded version of the PPower urinal for the treatment of urine and the production of electricity. How this concept works, instead of having a huge microbial fuel cell to treat waste, we have multiple small microbial fuel cells within boxes. So each box had about 22 small microbial fuel cells that were submerged into the urine liquid or wastewater. And then these boxes were stuck together like we're stacking batteries to increase the voltage or the current. And then these boxes, the way they were stuck together, they were feeding on each other. So the effluent of the one was the influent of the other. And this whole process, not only it was producing enough electricity that was stored into the energy harvester and discharged at night, but also it was cleaning the urine throughout the system because of its cascade configuration. So that is the basis of how the PPower system works. And moving on from pilot scale to commercialization. So PPower system, through funding from Bill and Melinda Gates Foundation, went onto commercialization using the social enterprise Microbial, which aims to make the PPower technology available to the market soon. So this is in the UK, but there is another company in the States, in California, called Aquacycle, which what they do in a similar context like PPower, they stack microbial fuel cells together in shipment containers, as you can see from the film over there. So each of these boxes that you see that are like car batteries, they have multiple fuel cell anodes. Over here, where the electroactive biofilm forms on it and generates electricity whilst treating the waste. And the Aquacycle has partnered with many industries in the States, with dairy industries, brewery companies, like soda, wastewater. So they treat a very vast range of wastewaters from their collaborations that they had, and the system is working great over there. So these are examples of how technology which started from the lab in 1911 turned into a commercial entity right now in 2022, and this is the progress of it from the lab to pilot to the field. So moving on into another technology, which is the Microbial Electrolysis Cells, which is a newer technology that, again, is using the same principle, but is applied with voltage and split hydrogen, so generates biohydrogen, and is using less voltage than actually water hydrolysis uses. So here in Newcastle University, Microbial Electrolysis Cells started from Dr. Heidrich in the lab years ago with the idea that it can be retrofitted into activated sludge into wastewater treatment tanks. And in the middle, you can see a microbial electrolysis system that has the anode on the outside and the cathode on the inside with the sampling port for the hydrogen, with the idea that it can be put into the tank. And this was done by the team, and it was the world's first pilot scale microbial electrolysis cell. So the systems, like cassettes, microbial electrolysis cells, were sitting in wastewater tanks, and they were generating about 0.6 liters per day of pure hydrogen, and it operated for a year. And even during the cold months, it was still operating fine, and recovered around 50% of electrical energy. And then the other pilot company, not to improve the technology and make it into a product that can be used from the water companies. Some pilots work better than the others, but the whole concept is that every time the system was getting better and bigger as well, which reached now to the pilot scale 4 and 5. So this one is an idea of where a microbial electrolysis cell can sit within the wastewater treatment process, and through the work from Dr. Daniel Lester, we can see here that the ideal location for this system is to be fed on return sludge liquor that comes after the centrifuge process of the treatment process. And this can work really well. The microbial electrolysis cell can work really well on return sludge liquor. And as you can see from the numbers here, it can recover the load remove, and it can also save costs compared with the activated sludge process, because this return sludge liquor would otherwise end up going back into the activated sludge process to be retreated. Right now at Newcastle University, we are at pilot 5, which we have at the BWISE facility, which is biological engineering wastewater innovation at scale. And as you can see here, we have 3 meter cube microbial electrolysis cells that we want to make operational through additional funding. So this is in collaboration with Northumbrian Water. And basically the technology right now sits at about technology readiness level 6. And we want to take it to a technology readiness level 9, of course, so it can be deployed in wastewater treatments all over the UK and hopefully the world. So one way that we are trying to do that is through a collaboration with Royal Haskoning, which right now I'm funded from NBIC to do an innovation placement here at Royal Haskoning, with the purpose of this placement to perform a pilot market research with 3 northern water companies in order to understand what the water companies' expectations are when it comes to microbial electrochemical technologies, and find that entry point for the technology in the UK wastewater treatment plants. Because, as you know, Royal Haskoning is a company that brings innovation into commercialization, and they're the ones that they produce the Nerida process that was shown in the previous presentation. So I hope I have given you an overview of the microbial electrochemical technology and how this can help us reach net zero in the wastewater treatment process. So I welcome any of your questions now.
Great, thank you, Pavlina, for a really interesting talk. We've had a few come in, and this one's a 2-parter, so I'll do it one by one. So the first one is asking, have you done a life cycle analysis for your approach? And the reason they're asking that is they're wondering how the electric generation at this relatively small PE level compares to, for example, the generation of electrovoltaic power.
So, but personally, in none of the groups that I work, we have done a life cycle analysis, but there are publications out there that do a life cycle analysis, I think, on microbial fuel cells, but I'm not sure at what scale. I can't remember on the top of my head at what scale, but yes, there are publications out there about it, about the life cycle assessment.
Right, and the second part is, with the relatively long HRT of almost a day, do you think that the limitation can be overcome?
Well, that's a really good question, actually, and yes, we've seen through the studies that we reviewed in that study with Hannah that depended on different geometries and different materials that were used for the microbial fuel cell pilots. And this is the average between all the studies that we reviewed, and we believe that in order to overcome the HRT limit is that if we can combine the technology with something else. So the microbial fuel cell system or the microbial electrolysis system can complement other technologies within the wastewater treatment process rather than it being a separate entity.
Right, and the second question had come in, is another 2-parter. The first bit is, what's the most critical parameter that needs optimization for wider implementation of the microbial fuel cells?
That's a brilliant question. I would say the simpler we make the system and with more cost-effective materials, the easier it is to be adopted by the developed countries. Whereas if we are looking for the wastewater industry, we will need to be more look more into better performing materials, whereas at the same time keeping the technology simple, because neither the wastewater industry wants something complicated with cables coming out of it and not being able to put together or maintain it, and neither you want to put a system in the field that the locals cannot maintain it either. So one thing is we want the system to be simple, and the other thing is the materials to be as cost effective as possible.
And the second part of that question is asking about how much maintenance does the toilet setup demand?
Oh, that's a good one. So for the ones in Africa that I work with, we were going there around 2 times a year to maintain the system, but we had people on the ground that when we were going there for the installation, we were training on the system. So they were taking some ownership of it. They were able to update us when things were going wrong. So we're advising them. But yeah, I would say within a year, 2-3 times you need to visit the site for maintenance. But the maintenance wasn't about the fuel cells. The fuel cells were right. It's about the peripherals. For example, in the one in Nairobi, we had mice infestation into the PPower boxes. There were mice chewed on the electrodes and built the nests within the boxes because it was warm in there. So something you cannot predict unless you do pilot studies.
And the last question is more kind of a looking forward aspect. Do you think, how far away do you think we are from being able to make a significant contribution to our energy needs via these routes? And what do you think it would take to accelerate it?
So first, what it takes to accelerate it, I will start from the last one. To accelerate, we need the uptake from the water industry. We need the water industry to understand that this is a viable technology, and we have proven it in pilot studies. So they need to trust the process and be more open to innovation. It's a sector that's a risk-averse sector, and this is what I'm trying now to do to achieve with my innovation placement, because we are academics, we are researchers, and industry speaks a little bit different language than us. So we want the help of companies such as Regal Haskoning to come and teach us and see from them and learn from them how we can bring our knowledge and combine it with industry. Because what we need right now is the uptake from industry and be more open to innovation. So hopefully by the end of my placement here, I'll be able to get some answers into that. So if you can repeat the first part of the question, that I'm not sure if I answered.
How far away do you think we are from being able to make a significant contribution to our energy needs?
So this one, again, yeah, it falls back into the uptake. But examples such as Aquacycle instead are making brilliant steps towards that, because they are partnering with water companies. They are partnering with them, with their clients over there, and they show them that this technology is viable and it works. And from updates that I usually see from their LinkedIn, they are doing great work over there. So yeah, it's the industry to trust the process and give some confidence and trust in the technology.